that I show. It's trying to get a beam splitter. Now, all a beam splitter does is take your coherent light source and split it into two. So half of the laser goes one way, half the laser goes the other. Both of these laser beams are going to hit two mirrors. And then they'll be reflected because they're mirrors. And when these lasers recombine, it can either be in phase, which again means that the peaks match the peaks, the valleys match the valleys, and so we get the original laser beam back through the experiment. However, they could also interfere destructively, and in this case, they would cancel out. So the idea here that Michelson-Morley had is that at different times of the year, the effective, let me see if I can point this out. The distance here versus the distance here would change. And that's because the speed of light would be changing. So it might be moving faster this way versus this way. And that change over the course of the year would cause this final laser beam to get brighter and dimmer. That's the idea. And that's the idea behind the Michelson-Morley interferometer. So some of you may be wondering why you've never actually heard of this luminiferous ether. So this was actually, the Michelson-Morley experiment is the most famous null result in physics. There is no luminiferous ether. As we now know, the universe is largely a vacuum, and light's able to propagate or move through this vacuum. And this is a really important result for many reasons. It destroyed many PhD theses about the ether, unfortunately. But it made an important man, Einstein, rethink about the theory behind light and gravity and connect a lot of pieces that had not been put together. But back to our story, we're here to talk about gravitational waves and LIGO. So now looking at this image of Michelson and Morley's experiment in the late 1800s, this image may make more sense. So this is LIGO, and it is a Michelson interferometer. And it stands for the Laser Interferometer Gravitational Wave Detector. It uses this exact same basic principle that Michelson and Morley did to detect variations in the speed of light. But today we're trying to detect small variations in space-time itself, ripples through space-time. In Michelson-Morley, in their original experiment, the arms that you see here were only about 30 feet in length, which is pretty sizable. But today, these arms are actually 2.5 miles, and they're able to detect fluctuations as small as 1,000th the size of an atom, which is a lot more sensitive. They're in fact so sensitive. So there's two LIGO instruments. One is in Washington, and one is in Louisiana. The one in Louisiana is near the school, Louisiana State University, which is well known for its football. And it's actually so sensitive that they have to stop doing measurements when LSU has a football game, even though LSU is 30 miles away, because they can hear everyone cheering for their football. Yeah, it's pretty impressive. So now that we understand the basic shape and how this interferometer is working, we're going to next try to understand what exactly we're measuring, what are these ripples in space-time, and what's causing them. I'm going to stop here and take questions.
Why does Michelson-Morley have two things? Like for this return, can they just rotate the arms, and at one point they'll be with the ether, and when they rotate 90 degrees, they'll switch the arms?
Yes, that is fair. So, well, I'm not exactly sure it's fair. I don't think this was, I think first of all, the cable was like not able to rotate because we needed to keep it incredibly steady. Oh, can you repeat? Oh, I have to repeat the question. Okay. So the question is, why do they actually have to wait a year? Because what really matters is that the two arms are perpendicular. And so with time, if you just rotate the system itself, then that should work. I'm not exactly sure why, because you're correct, but my one guess is that they were unable to actually rotate because it's so sensitive to these very small variations in the system.
Okay, if it's so sensitive to the pixel football game 30 miles away, what about seismic activity?
Yes, that's a great question. They do pick that up. And so the question is, LIGO is now so sensitive that they're able to detect, for example, a football game 30 miles away. So surely they're able to detect other seismic activity on the Earth, and that's completely correct. However, they have terrific mathematicians who are able to model a lot of this activity. And so that helps eliminate most of the noise. And the rest of the noise is actually eliminated by having two systems. So I'm just showing you here the one in Washington. And then the other system is actually in Louisiana. So they're also going to look for correlated signals. In other words, they're going to look for a signal both in Washington and in Louisiana. And then that's further proof that that's a real physical signal and not just seismic activity. Any other questions?
What kind of a laser is used, do you know?
Now, I do not know what LIGO is using. So when I was in Morley experiment, didn't really use the laser, just used a coherent laser. But now, I don't know how large the laser beam actually is. Any other questions? Yeah.
Why is the second O in LIGO not a D?
Oh, sorry, it should be observatory. But it's also a detector, so. So the idea is an observatory, let me explain actually. So it's a detector in the sense that they want to detect a single gravitational source, which they have done. We'll learn about that later. However, now we're excited to make it a real observatory in the sense that it's going to detect hopefully multiple events over the course of the next few years that it operates. Any other questions? Sorry. Oh,
Actually, the length of the arms is 3 miles or something.
yeah. It's 2.5 miles.
Cosmic scales, it's nothing. It's far enough, it's long enough distance to measure. These effects be seen.
Yes, that's a great question. So the question is that the length of the arms is actually only 2.5 miles, and compared to the size of even our solar system, that's incredibly tiny. So how is this measuring a cosmic event? And so what's going on is that we're actually able to probe even further because we're looking for an interference pattern of a relatively small wavelength over a very large arm. So that fraction is incredibly tiny. It helps us measure the very tiny change in space-time itself. So we don't need an incredibly large system to measure this incredibly small change. However, it needs to be fairly large. So 2.5 miles is incredibly large for a laser propagate through. Any other questions? Okay, I will switch over.
All right, get a sound check first. Loud and clear?
Yeah.
Great, so let me first introduce myself. I'm Consul Daina. I'm a graduate student at Harvard. I essentially work on cosmology and particle physics.
Speak into that.
Okay.
Yeah.
All right, so let's make closer to that. So I work on particularly on the problem of missing matter in the universe, the so-called dark matter. And at the very end, if you are also interested in dark matter, you can ask questions. Today's subject will be gravitational waves instead, and Ashley actually made a really good introduction into the physics of waves. And I will take the discussion from that point and basically walk you through what now a gravitational wave is and how we want to use these gravitational waves to astrophysics, essentially. The very fact that she said it was a detector, now it's an observatory, that's an important statement because we have so far regarded these very long current interferometers as detectors because we were trying to detect something. Now that we have detected something, now we can use these detections as essentially messengers to understand the universe. So now I will walk you through these concepts. But again, let's start simple. So I will take you back a couple of centuries to start the discussion. If you go back, maybe not so far, but maybe like 4 or 5 centuries ago, there are ideas in science which we take as granted, and one of those is the understanding of celestial mechanics. Essentially, if you think about how a planet moves, for example, about 5 centuries ago, this was just subject to prior belief, essentially, and it was a matter of religion and philosophy, how planets actually moved and stars, of course. But Newton, a British scientist back then, was the first person to make up a theory. When I say I don't mean really make up, but constructed, a scientific theory of gravity. And in fact, this scientific theory is still the basis of our understanding of gravity, with slight modifications which I will come to. But there is a problem with this understanding of gravity, which is that Newton's ideas, Newton's theory of gravity, which I think we published in 1687, so almost like 4 centuries ago, this theory had a problem. It predicted that causal relationships, when I say causal relationship, I mean there is a source of reasons, a cause, and an effect that is as a result of that cause. These cause and effect relationships were simultaneous. In other words, they could happen anywhere in the universe at the same time. Like a cause could result in an effect almost at the same time. So I will give an example. So if you think about the solar system, here I made a schematic representation of that. So as you can imagine, the yellow circle is the sun, the blue circle is the Earth, not to the scale, of course. So I will first want to ask you a question. Let me get a show of hands. Let's have a thought experiment. What happens if I were to, using my supernatural abilities, if I were to take the sun out of its position? What do you think is going to happen to the trajectory, the motion of the Earth at that time? Will it continue to move in a circle, or roughly a circle? Actually, it's in a ellipse. Or will it start to move in a straight path?
I think it'll continue to move in a circle.
Move away.
Great. For how long?
For 8 minutes.
Great, some actually steady. Alright, so yes, indeed, it will not continue in a straight line, at least for some time, for about 8 minutes. 8 minutes is the time that light takes to reach from the sun to us. And you will see that in the next slide, actually, that Einstein, so there, I'm now going to jump to another theory of gravity, and this theory is now going to predict that cause and effect actually takes some time, some finite time, not zero, some time to actually propagate through space and time. And therefore, causal relationships cannot be simultaneous. That's Einstein's view. This is brand new, actually. Einstein published this theory in 1950. Now we jumped almost 3 centuries. And Einstein's theories now form the basis of our understanding of gravity. In Einstein's theory, the space and time can be bent. This is a very abstract notion, so I can't really go into detail. But basically, what you should have in mind is the Earth sitting, and basically, because the Earth sits at a given point in space, it kind of bends the space and time around it, so as to cause the objects around it to remain in orbit around the Earth. Of course, here what you have in the picture is a 2-dimensional view of that. we live in a three-dimensional world, and in a 3D world, I cannot actually show this on a projected image. That makes it very abstract. But taking faith, at least for the moment, that the space and time in this theory can be bent, and that's how gravitational interactions, the fact that I feel the gravity of the Earth, that's how Einstein's theory actually accomplishes this. And why am I telling you this? Well, the idea is to understand gravitational waves, and in order to do so, we have to understand gravity, at least our current understanding of gravity. So here I'm just listing 3 items that made Einstein so famous. Einstein predicted, Einstein published this theory in 1915, but of course he did not become very famous right the following day. It took some time for other physicists to confirm the predictions of his theory. On the left, for example, you see ellipses, but these are ellipses whose angle with respect to the sun that you see in the center changes, which means that if you have a planet that revolves around the sun, its orbital motion, which can be characterized as an ellipse around it, it will shift as time goes by. That ellipse is going to shift around the sun. Now, this is a unique prediction by Einstein's theory. This is not predicted in Newtonian understanding of gravity. This is the first thing that made Einstein famous. The second thing is the solar eclipse of 1919. In 1919, there was a very famous solar eclipse, which allowed astronomers to go ahead and measure the positions, the precise positions of the stars right next to the sun. And as a result, people were able to actually confirm another prediction of Einstein's theory of relativity, which is the bending of light. Again, this is a very abstract notion, which unfortunately I can't really go into much detail, but feel free to ask questions about. That's the second prediction. The last prediction that I wanted to discuss is the gravitational change, the change in color of light due to gravity, essentially. And here, let me give you a historical fact. Basically, these 2 pictures are taken from our physics department here in Cambridge, from Harvard Physics. At the top, you see the professor Pound, and in the bottom, you see his grad student. And as you can see, the professor is working in this warm office or maybe laboratory, and the grad student is in the basement doing the measurements, as is usually the case. So this actually has a history to it. Basically, what they did is they drilled a hole into the apartment, the physics building, and they measured the minute change in the color of light due to gravity. And this was a very unique confirmation of another prediction of Einstein's theory. But there was one that has not been detected so far, confirmed so far, until last September. And that was the prediction of gravitational waves. So let's now go on to discussing what a gravitational wave is. Well, basically, if you imagine the plane of the screen now, so I'm waving my hands along this plane. So you imagine essentially the board. And imagine a direction perpendicular. So basically going into the board. Okay. So if you imagine there to be a gravitational wave, just like Ashley mentioned, going into the plane, okay, that's going to cause basically assume that there are some balls on the board, and that's ingoing gravitational wave will cause these balls to be deflected in these 2 manners. There are 2 independent ways in which this could have happened, so I'm giving both of them. We call these technically polarizations. In other words, there are different ways in which the balls on the board could be deflected by a passing gravitational wave, and these are the two such waves. So I'm just giving also the axes here. So you should imagine the gravitational wave to be either going in or coming out of the plane. And one thing that I should definitely make clear is that this is not to the scale. Because in LIGO, we are measuring a distance, a change in the distance that is 1,000th of the proton's radius. That's an extremely small distance. Of course, here I'm exaggerating things for you to be able to see it. But this is a very, very precise measurement that LIGO makes. And the second question is, okay, now we've got at least a rough idea of what a gravitational wave is, or at least how it affects the surroundings around us. You might be wondering, okay, like what actually produces these objects or these waves? Essentially, if you have two very massive and compact, when I say compact, I mean dense essentially, two very dense stars. I don't want to use the technical word for it, but for those of you who are interested, it's called a neutron star. It's a star that is made up of neutrons. That's why it's very dense. If you take two of these neutron stars and let them revolve around each other, essentially in this manner, as they spiral in, they will be producing such gravitational waves that I just showed you. And as you can see in this image, in this artistic image, of course, you see the space-time bent, and that bending is due to, oops, I think I dropped this. That bending is due to the passage of gravitational waves. And the last slide here. Now you may be wondering, okay, what is this good for? Like, how can we actually use these gravitational waves? And I don't mean like technologically, at least for the moment, but rather like astronomically. Like, how can we learn more about the universe using these guys? The answer to that I will give is the fact that in the universe there are regions which are opaque to our telescopes. When we look at certain regions in the universe, especially in our galaxy, but elsewhere in the universe, we see patches where the so-called dust in the outer space blocks the light so that the light cannot reach our detectors from the emitting object, whatever that is in the background. So we can use these gravitational waves actually to see what's inside this opaque region. And these usually will turn out to be either colliding or revolving neutron stars. Okay, I will stop here and take questions. Yes.
Okay, according to Newtonian physics, two balls rotating against each other would forever rotate at the same distance all the time and not spiral in. I would assume the spiraling in is being due to loss of energy from gravitational waves being dissipating.
Yes, that's it.
Okay. The other thing is, you now have a detector. How do you get an image? How do you know where this is coming from? So you have to have an array of them?
Yes. So here we have two.
Can you repeat the question, please?
Okay. So the question is, so the first question was, in mechanics, we have photons rotate around each other. The Newtonian theory of gravity would predict that these two eventually merge and collide. And yes, that is true because in Newtonian mechanics, there's no such thing as gravitational waves. And in general theory of relativity, the second theory I mentioned, in that theory, there is energy loss due to the gravitational waves. That was the first question. The second question is, how do you see where a particular, how do you infer, let me say, where a particular gravitational wave is coming from? And that's an important thing because if you want to have an observatory, you want to eventually be able to point to a particular direction in the sky. Okay, say that gravitational wave came from that direction. So for you to be able to do that, you need multiple detectors. and we currently have two of them. And well, there are actually more, but the other ones, like there's one in also in there's the in Italy. Okay, there's a third one in Italy, but that was not sensitive enough to get this signal. So the detection that we will talk about at the end. So currently we only have two very sensitive detectors, and with only two, you can only constrain the direction to roughly strike. But if you have a third, you can do triangulation, the so-called triangulation, to actually point to a particular direction. And the more detectors you have, the smaller your uncertainty about the direction will be. Yes, let's go clockwise.
So you say gravity is a very weak force. Relative to what? I don't think that gravity is weak. What are you comparing it to?
Great, okay. So I think that's a great, so, right, I should get used to this. Basically the question is, why is gravity weak? And she rightly said that, she thinks that gravity is actually not weak because, we all feel the tug of the Earth. And from everyday life, it's hard to realize this. But I will just point out one thing. So gravity might be strong to make sure that they're always on the ground as long as you're doing bungee jumping. Or like the very fact that you have a reaction from the Earth upwards, so that you are not accelerating your velocity is not changing. When I stand still, I'm not accelerating towards the center of the Earth. Means that there's a reaction force, and the ground is pushing me up. And that pushing actually is what we call electromagnetic force. Now, electromagnetic force is orders and orders of magnitude stronger than gravitational waves. And because of this, we think that there are regions in the universe, because the electromagnetic force, the other force that we all feel from the ground, because that is so strong, light cannot arrive at our detectors from certain regions of the universe, and gravity or gravitational waves will. Yes.
Okay, so when the examples of waves, sound and water waves, and like when the sound goes through the air, I think of the wave as being over here, even though the person already made noise. I think of the air molecules are pushing, they're getting squeezed together and back apart. So I think of that local effect in the air molecules keeps the wave going. And with the water wave, I think of the water going up and down, and something happens that it keeps the wave going. And when light's going through, I think of that as like somehow Maxwell's field equations are saying why that propagates. So is there a field theory for the wave that's in the gravitational ether, whatever it is? Is there something that I should think of as making the wave propagate?
Yes. So the question is, we have seen so far 3 examples of waves: the sound wave, the surface wave, what is usually known as the ocean waves, and third, the light. Now we're introducing the fourth one, the gravitational waves, and the question is there, like in each of the previous 3, there are underlying physical models. Is there a related physical model for gravitational waves? And the answer is yes. The model for that is essentially Einstein's theory of general relativity. So Einstein's theory of general relativity basically is a set of equations. And once you solve these equations, you get an understanding of how excitations in space and time can propagate. And just like we solve, as you said, the Maxwell's equations for electromagnetic interactions or waves, we solve Einstein's equations to understand how gravitational waves evolve over space and time.
Right. So
currently people are talking about LIGO experimentation, claiming that for the first time they're observing gravitation. But a few decades ago, it was already deduced in the example of binary pulsar in early 1970s. So what happens is two neutrons start spinning around each other, they lose energy according to general relativity. Once they lose energy, the orbital changes subtly, and based on the observation of the subtle changes of the orbit, you can deduce gravitation, right?
Yes.
That's considered as something indirect observation. Do you think that's a good enough observation to confirm gravitational wave on those the binary pulsar
Right.
observation?
So the question is, a couple of decades ago, we had the so-called indirect detection of gravitational waves, and that was essentially accomplished by measuring the period of orbit, the orbital period of two compact stars, the so-called neutron stars. As they orbit around each other, they lose energy to gravitational radiation, and their period changes. And astronomers several decades ago actually inferred indirectly the existence of gravitational waves, because they said, okay, if gravitational waves exist, I mean, if that's reality, then these the period of these neutron stars actually should change, and they actually saw that in the data. So one could consider that as an indirect evidence for gravitational waves. But in physics, you usually need orthogonal, in other words, like independent ways of making a claim. And that was one way. Now this is a more direct way. And the best thing is to have both of them.
Right. Secondly, in addition to the gravitational theory Newton and Einstein, can you just briefly mention how the concept of gravity on string theory is different, very different from the concept of general relativity?
So in string theory, you build things from top to bottom. It's a completely different way of approaching the problem. I don't want to go much into detail because it's very abstract, but I'm happy to discuss afterwards. But let me just summarize it in 2 seconds, two sentences. Sorry. Basically, the idea is you don't try to understand, this planet or that planet and try to fit your model to that. Instead, you start with the statement that the universe is some n dimensions, and there are zillions of forces in this universe, and you try to reach this universe that we live in from that huge hypothesis that can be tailored to anything essentially. I'm not trying to degrade string theory in any ways, but I'm just telling you that the methodology is very different.
I think we're going to have to take a break for intermission at this point, but feel free to come down and talk to them. We'll have about 10 minutes, and then we'll get to the second half. Thank you. Yeah. Yeah. It should be plugged in, no? Oh, maybe not. Oh, yeah, it should be plugged in.
So
No, but, so I've heard this theory is that black hole is so dense, and space is so much.
It's just that
Horizon is the edge of the space time.
I know that there are many constants that we can so, but it's very hard to actually So the best part that happens there is I'll come here and like make sure we have everything set up, and that point is going to take long for us. This is too good of an opportunity. Oh, great. Yeah.
What's the
I was like sitting on the floor. I mean, I doubt they're out now, but like I was sitting on the floor, I was like, oh my god, I hope it like. I know, I can
You seem like you're something.
What? I think I don't know how to practice softball on place.
That's a good reading.
Yeah. Yeah, it'll be good. I was very sad not to be there.
Sounded like you had.
I was at a wedding, so. Someone, my best friend in lab. No, I mean, I was at the wedding of my best friend in lab, which I guess was exciting. She wasn't doing exciting things. Katie, you're so lame.
This past
Things are changing. So if I were to like keep the consideration points, how we change mass, can we change how frequency changes is a function, but it will not change
I
that.
was still in denial and I still in my head
I just keep reminding myself that I'm
They will, yeah. Sorry.
Yeah, as long as you
Yeah, that is just
oh, there's a final story.
that's what I was thinking.
Yeah.
What do you do if you don't have you have 5 minute stories? And they're all lies too. You don't actually have a path. You have just decided. I'm the
So basically, the idea is if you
Hey, come on, kid. I'm tired of being
That's so true. Well, we have like all these people trying to come here. I'm like, so really, yeah, you guys are the I did that already.
like now she's doing a bunch of questions. So whenever I just if you want to arrange I'm trying. No. And I get to pick which jobs I do. So it's during I don't know how to do it on this. Pretty much what I'm doing.
no, I mean,
Well, I've been doing
they're like zillions of galaxies. The hope is that I guess they are taking
I know, it's probably some 7 billion.
All right, we'll get started again. Thank you guys for all your great questions during the first half of the talk. I also just want to briefly remind you we have a survey up front. So please, if you haven't already, grab one and take the time to fill it out. It really is helpful to both us as organizers as well as the speakers.
nice. Okay, so it's me again. I will move on now this time with hopefully a more visual introduction to black holes. So, I mean, it's hard to make a presentation on gravitational waves without mentioning the word black hole. It's just what people are curious about. So we included that in the discussion. Not necessarily because they're central to the topic, but you will see that the detection of light actually do relate to such objects. And hopefully I will finish this section by showing you the actual detection plot of LIGO. And we will take it slowly to try to understand the details, but not go much into the All right. So here there's, I just wanted to start with a popular picture. So it's the, how many of you have seen the film Interstellar? Yeah, the majority. Otherwise, like, please do see it. It's great. Oh, I know. This second time I'm doing this. Just a second. Closer. So this is a picture of a black hole, but the thing is, you actually can't see a black hole. So what you are seeing is essentially a stream of photons and light around the black hole. You can't actually see the black hole by definition. The fact that it's black means that you should not be able to see it. And that's how we visualize it. But the important thing is, in the film, they were so careful about simulating how a black hole should appear to the human eye. So this is a, well, I wouldn't say 100% accurate, but close to being accurate representation of what we would see if we were to be very close to a black hole, and second, be fool enough to look at it instead of running away. So let's start with I'm trying to understand what a black hole is. And the first thing I should say is black hole, you should imagine black hole not as a solid object, but rather a region in space. So not an object, like not something that you can touch or you can feel, but rather it's a region. And it's a region from which nothing, and when I say nothing, I include light, I include information, I include myself, I include you. And nothing can escape, okay? And I really mean it's like there's essentially in physics, there's nothing that can escape a black hole. If light cannot escape it, nothing can escape it. And but you're free to fall into it, so there's no problem with that. So we will, if you fall into it, we will be seeing an ever-aging copy of you slowly fading into darkness. So yeah, that's a nice way to end. But basically here, that's what TARS is doing by escaping into the black hole. It's clever in that sense. So TARS is, by the way, is the robotic creation from the film. Okay. All right. So now a couple of words on how a black hole can be formed before we discuss how they actually come together and merge. So the black holes that you are probably familiar with are what we call the stellar black holes. So these are essentially remnants of stars. Stars, you may not be familiar with this, but stars are just like humans. They have a particular lifetime. So they are born out of gas in the outer space. And they spend a couple of billions of years just burning happily their hydrogen into helium. And then finally they die, they lose their fuel, they die. And if they die, sometimes if they are massive enough, if their mass is high enough, they eventually collapse into what we call black holes. That's the first type of black hole I wanted to mention. But there's actually another interesting type of black hole. If you imagine now these very small stellar type black holes coming together and merging over cosmic timescales, then you might imagine that there will be a huge black hole, some billions of solar masses. Like when I say solar mass, I mean the mass of the sun, and multiply that by a billion. It's a huge number. And we think that there are such supermassive black holes at the centers of galaxies. That's the second type. The third type is not, it's more abstract, so I won't spend much time. If you think about the very early times of the universe, like the first second or so, we think that the universe in the beginning was very hot and very dense. In this very dense environment, you could imagine these density irregularities to collapse into black holes. These are very old black holes, some 13.8 billion year-old black holes. And that's the third type. Ask me questions later if you're interested. Now, the idea is we will bring together these black holes. Essentially, what the way we will produce gravitational waves is you need these black holes to revolve around each other and eventually merge. And if they somehow, in the cosmic sense, lose energy somehow and produce a binary system that, where black holes actually revolve around each other, you will remember this type of motion from the previous section because I used it to show how a gravitational wave was produced. Basically, if you have two black holes orbiting around each other, they will produce gravitational waves. And that will depend most of the time on how massive they are and their other properties, like how their orbital motion is centered, but I won't go into such details. But the end product is essentially an inspiral, what we call an inspiral. So these compact objects slightly lose energy over time, and they come closer and closer to each other, and at some point they have to somehow merge. And that merging will bring us to this detection that was recorded last year in September. So I will slow down in this slide and try to walk you through the observation. So basically, we heard in the scientific community, we started to hear about the rumors back in November because this is a huge deal. This was the last confirmation of the last prediction of the general theory of relativity. So it was like the last piece in a puzzle, if you think about it that way. So it essentially closed a chapter in astronomy or in physics in general. So what you're seeing here, basically, there are two features. Let's just think about the one on the left. So basically, the one on the left comes from one detector. So there's one in Hanford, Washington, and the other one, as I was just telling you in the previous section, there's another one in Livingston, Louisiana. And let's just concentrate on the one on the left, so the red line that you see. So the horizontal axis here is time. So the time runs from the left to the right, okay? So if you move your finger to the right on the line, you essentially are looking at the change of something, which I will come to, as a function of time, okay? Now, on the vertical axis, I've removed the units. It's not extremely important. I will just tell you that it's an extremely small number. I've removed, the units, but the units had an extremely small number in it. So although you see 1.50, it's actually an extremely small number. So you can assume that this is this times a very small number, essentially. Okay. Now, what you're seeing on the vertical axis is the change, essentially, of the arm length, or something that is proportional to it. Like, don't really worry about the details. It essentially characterizes how much of a change there is along a given arm of light. And if you look at the very far left of the plot, you will see that there's some noise. There's nothing particular to be seen. But at some point, a coherent picture starts to kick in. It's something that oscillates. The second grid, like starting from the second grid line, the vertical line, you will see, actually I have a pointer. Well, this piece is massive, okay. It's the largest pointer I've ever seen. Starting here, actually, the second grid line, there seems to be some, well-defined oscillation here. Here, there's this noise, but here, you actually see some oscillation. And basically, what you're seeing is some gravitational waves travel through the Earth, hit the arms of the LIGO, and essentially produce this interference pattern that is then recorded. And of course, it's not so easy if you take the data at face value. It's not so easy to see this. You have to process the data. You have to filter out the noise. There are sources of noise that we won't really go much into detail, but statistic noise is one because it was asked, but there are other sources. So once you filter those sources of noise out, then you get this nice shape. And now let's connect this to what I was talking about. So if you go back to far left again, you can imagine here that the two black holes are far apart. So in fact, the gravitational wave that they are producing is not strong enough. But as they move towards each other, towards the final moments of the in-spiral, finally resulting in a merger, they produce actually observable gravitational waves. And this is marginal detection. Of course, it could have been much stronger. We would have detected it years ago. We haven't because we were unlucky, because the LIGO actually has been operational for years, and we haven't had any detection so far until last September. And what you see on the right is essentially a little copy of this. So I won't go much into detail. So because the legs of the two interferometers are not aligned, there's a shift. So you take this and shift it in time slightly, and you get this picture, but they are consistent. And the fact that they are consistent is important, because if you take some fluctuation, some noise, let me give an everyday life example. If you look at your television and unplug the cable, what you will see some noise. There will be black and white fluctuations on the screen. You can take this to be like the fluctuations here. Now, the thing is, once we have a strong enough signal, that noise will be overcome by the strong signal of the gravitational wave. And the fact that we see the strong signal in both assures us that we are seeing something real. If you were to see it only in one, you could think that some very lucky combination that you see on the screen could be something like this. But the fact that you see two independent televisions showing the exact same coherent picture, that is very, very unlikely by chance, for it to happen by chance. So we now know, up to some, of course, confidence level, that we are looking at something real. All right, so I will now play this. So this is going to be the sound of this waveform that we call a chirp. Chirp is just the sound that the birds actually make. So you can think that the birds actually can hear or can communicate with black holes. No, I'm kidding. Okay. So as the movie moves, you see that there's something, the color changes as a function of time as time goes by towards the right. So at that point, let me replay that. At that time, you will hear the relevant sound here and here. That's the sound that the detector hears. Of course, this is not a sound wave; it's converted to a sound wave. And the thing is, what you should realize is its frequency is increasing as a function. As we advance, as time goes by, the frequency that we hear increases. That's why it's called a chirp. So it's not a constant frequency, but rather an increasing frequency. Well, why is it increasing? Because the two black holes are coming closer to each other, and as they come closer towards each other, their periods about each other is shorter, and the characteristic frequency associated with that is larger. Okay, I want to move. All right. Yeah, so, and that's the last plot I want to show, and I can get your questions. So I've already showed the upper raw, so that should not be new. Now the bottom raw is new, and that is just to emphasize the level of agreement between what we expect from gravitational waves and what we actually observe. On the bottom row, you see what we expect, what our models tell us that we should be seeing in this observation. And on the top, you see what we actually observe, and they are very similar. And this gives us additional confidence that we are looking at something real, and on top of that, it confirms the predictions of general theory of relativity. So that's another applause for Einstein. Okay, so let me get more questions.
So why is it that black holes that do they merge, but neutron stars don't?
Neutron stars also do.
Okay. Well, and then it kind of leads to another question, which is like, I understand with neutron stars they do kind of like go. I mean, like they get closer to each other and closer until they basically hit each other, right?
Yes.
Well, if a black hole is taking in light is energy. So I guess I'm just missing, I feel like I'm missing some kind of piece of like a black hole sucking all the light and energy, and how is it losing energy?
Where's the energy go?
Okay, so so let me repeat the question. The first question is, do neutron stars also do the same? And the answer is yes. We expect gravitational waves from both neutron stars and black holes. The second question is, how does black
neutron stars merge?
Yes, they do.
Okay, I got lost there.
The second question was, how do the black holes actually lose energy? Well, they lose energy not by radiating particles, but rather distorting the space and time. So that's a different thing. It's not that like nothing, well, energy can escape black holes. And in fact, there are ways, even without using gravitational waves, there are ways that you could try to steal energy from black holes, but that's a whole different topic. I won't go into detail. But using gravitational waves, that's very easy. Essentially, the black hole settles down into a stable form because once two black holes collide, it's in a very asymmetric state. So it has to throw away its asymmetries, and as it does so, it will radiate gravitational waves. And the same will happen for neutron stars.
I have a question. You say that all these lectures that we saw in the LIGO is because was a merge, right? Yes. So how often you guys that study these black holes, and how often do you expect this event to happen again in the galaxy? Because I kind of remember that the LIGO was made a lot of years ago, and nobody catch nothing, and somebody say, oh, let's go for more money to the government and let's make it better, and then is now in the when they upgrade, when we're able to catch something. But how often are you expecting to have these readings in these methods?
Right. So the question is, how often do we expect to see such events? And the answer is essentially that depends totally on how sensitive we are, because we think that such events actually happen every time, everywhere in the universe. If we were ultra sensitive, we would be picking up thousands of them per day, maybe. Like, because the universe is so large. Like, there are lots of binary systems, neutron stars and black holes, not just in our galaxy, but there are like billions of galaxies out there. The only thing is that it's very hard, practically speaking, to achieve such a sensitivity. So, realistically speaking, with the advanced LIGO, we expect something like a few in the next years to come, maybe 5. Of course, it depends how optimistic we are, but maybe let's say 10, but not like hundreds of thousands.
Is the only phenomena that you're trying to observe the merging of these binary systems that are collapsing?
Yes, so the question is, are these mergers the only things that we care about? Actually, there are other things, like, for example, there are supernova collapses, or collapses, and once the core of neutron star actually collapses, if that is happening asymmetrically, if it is a totally spherically symmetric thing, then it will not produce gravitational waves. But if there are asymmetries on the neutron star, it will also produce gravitational waves.
Okay, so if there are, at some level of sensitivity, like lots of these things going on all the times, do you think there's going to be an issue where you're detecting a couple of different events in different locations and getting interference patterns to filter it out?
Yes, we hope that we hit that limit somehow, because it's a very optimistic thing. That's, in a crowded field doing gravitational astronomy, it's such a far into the future idea currently, because we are so happy that we only saw one,
right.
And the fact that there's seeing many of them on top of each other, that's like heaven. But of course, we do the same thing when we look at, say, the galactic center, the center of our galaxy. In that picture, there are many stars on top of each other, but there are algorithms we use to filter those out.
2 more questions.
So the wave is being caused by the energy of these things spinning in on each other, or by the motion? Because once they, or just the gravity mass itself, once they're together, still it's the same amount of mass too. Now it's just one object. It's still not going to produce. Once these waves start, where do they stop? Maybe that's my question. So is it the actual speed of the motion of this thing through?
So the question is, how does the gravitational wave actually produce when they come into contact? And this ties back to what I was saying. So if there are, let's just, we've so far seen that once the black holes are orbited around each other, it is this motion that produces the gravitational waves. But imagine the case when they actually merge. After the point, after the point at which they merge, now we have a single object. But the problem is that single object is very asymmetric, and an asymmetric object will have a strong gravitational. Okay, this is technically speaking for interested quadrupole moment. So that will cause lots of gravitational waves to appear. And of course that happens as long as that type of asymmetry is present. Once that is shaved off, it won't produce gravitational waves anymore.
So I guess similar question around, how do you mean by symmetry? Is symmetry a shape, or is symmetry a density, or both? What kind of symmetry are you looking at?
So I'm talking about the symmetry. So first let me go technical and then I will boil it down. I'm talking about radial or spherical symmetry. So the symmetry, so if I'm sitting at the center of a sphere, if I look in any direction, if I see the same thing, that we call spherical symmetry. And I'm talking about spherical asymmetry.
All right, we should probably.
Okay. So, the next section will be on the electromagnetic counterparts from neutron stars, and actually we'll talk about her own research. Maybe. Let's see. I'm curious.
Okay. So first, let me clarify. You can think of gravitational waves as a different messenger. So if the universe is trying to communicate through this new phenomenon called gravitational waves, like hearing, for example, and now we're going to talk about seeing the actual counterpart to this gravitational wave, or seeing the event happen. And the way we're doing this at Harvard is we're using something called the dark energy camera. So this is the detector that's in Chile. This is the picture of the detector itself. So those rectangles that you see are actually CCD cameras. It's the same thing that's sitting in your cell phone right now, but easier and much nicer probably. And what they do, well, what we do, is that, and Ken just told us about this, LIGO will basically tell collaborators, look, we've detected gravitational waves in the last day or two, and now we want you guys to go see if you can actually find the light coming from these gravitational waves. And so literally, here at Harvard we have a group, so my group, Ego Berger is the advisor, we take control of this dark energy camera, we turn the telescope towards the very large area that LIGO has told us where the gravitational waves probably came from, and we try to find a counterpart. So we try to look for light in the form of basically a bomb in the sky. So why would we actually expect anything to happen? So we've been talking about collision of neutron stars. And neutron stars, maybe I should give a better reference to what's going on here. When really massive stars, so stars, let's say 10 times the mass of our own sun or bigger, collapse, instead of forming a black hole, so a stellar mass black hole, they can also maybe form a neutron star if they don't collapse all the way, if they're held up by neutron degeneracy pressure. If you have this, then you can have a binary of two neutron stars, and they will, in the same way that black holes do, they will in-spiral and eventually collide, leading to gravitational waves. The difference, though, is that these won't completely capture all of the energy, and some energy will get released, which will allow the fusion of heavy elements. And we're able to see this fusion with telescopes, and maybe with our own eyes if we look at the images. With kilonovae, which is the name of the explosion that we see for two colliding neutron stars, we mainly see very red light, so infrared light. So we wouldn't really see it with our own eyes, but we can definitely detect it with our telescopes on the ground. And we're able to actually see this for about, well, we haven't seen it yet, so we don't know. But we predict that we'll see this light for about 5 days. And that's long enough, hopefully, that we can look after LIGO tells us and try to catch the event. This hasn't happened yet, and that's because the two events that LIGO has detected have both been from very massive black holes. So we've completely ruled out the possibility that we've seen a neutron star collision. But LIGO is getting more sensitive, and so the hope is that eventually we will be able to see these kilonovae. We're even hoping as soon as a few months from now, LIGO is about to start its new, it works in semesters, and it's about to start its new semester, and our group will be following this up. But why should we even care about that? Why should we care about this fusion of elements? And so here I'm showing you perhaps a confusing plot. So if you think back to your days in chemistry, there's a periodic table of elements, and they've been color-coded in a special way. They've been color-coded based on how they're majorly produced in the universe. So the majority of hydrogen and helium in our universe was produced in the Big Bang, and that's the start of the universe itself. After that, well, we can ignore the cosmic rays. We see these yellow and green elements, and these are elements that are produced in stars. And so as we've learned, stars spend most of their life just fusing small elements together to make these heavy elements. And these get fused basically up to iron. I know there's some argument in iron, but basically up to iron. And past that, there's a question of, well, how do we get these heavier elements? It turns out that we need stars to either explode or merge to make pretty much every element more massive than iron. So here I've highlighted in orange, I'm calling them the products of kilonovae. However, to be totally clear, they also come from supernovae, and the technical term is called the R process for making a lot of these elements. And so this is where the phrase that we're all made of star stuff actually comes from. It's true. All of these elements that exist and make up each and every one of us have to come from inside stars, and these elements can only reach outside of their atmospheres by exploding or merging. And that's why it's so important that we find these kilonovae, because these are going to give us pretty much the only glimpse into a special process that makes these very heavy elements. And that's why we so desperately want to see one in hopefully the next few years. So that was my very brief interlude about what we're doing right now at Harvard, but you're welcome to ask me questions after the conclusion of our talk.
Oh, I'm sorry.
All right, so I don't have much to say. I'll just finish off the talk by giving you essentially an overview of what we expect to see in the future. And we took the story from Einstein back in 1915 and arrived at this nice discovery of gravitational waves last September. So what's next? Well, the thing is, now that we've detected a gravitational wave, we are all set to detect more and more of them, and finally try to understand the universe through the glasses of gravity. And that's the next step, basically. If we can statistically collect enough data on these mergers, then you will be able to, for example, understand how galaxies form. And because these stars, the mergers, will tell us where galaxies are and how many of them there are, and what are the processes that let these guys evolve. And they all essentially make up the big picture of cosmology. And I don't like text conclusions, so I will just conclude with this picture. So this is a futuristic picture of an idea. It's called e-visa. It's called evolved visa, but actually it's downgraded visa because NASA did not want to participate in it. So essentially this was a project between NASA and ESA, the European Space Agency. Now it got smaller because NASA couldn't find the money to participate in the project. But the idea is, now take LIGO, put it in space, but do it so that the arm lengths, well, they will not be constrained to be 3 or 4 kilometers anymore. Just make them as arbitrarily large as possible. As long as your laser is powerful enough, you can make them like millions of kilometers. So have these essentially floating around in our solar system with, of course, precisely controlled interdistances. If you can achieve such a system, then you will be able to probe much gravitational waves with much larger wavelengths. Now that will be important because we don't only want to probe stellar mass black holes, the black holes that are remnants of stars, but we also want to be able to probe, say, supermassive black holes that are like in our galactic center, the center of our Milky Way galaxy. If we want to probe such things, we want to go to much larger wavelengths. There's no way on Earth, and literally on Earth, there's no way to do this. So, so there's one way that you could go in space, but of course the other way is you could go deeper. In other words, you could make more sensitive instruments that will replace LIGO, or at least work along with LIGO. One such proposal, one such project is in India, and another more mature project is in Japan. So there are all these new generations of interferometers around the world that will hopefully in the next decade or so will be working together for us to understand the universe through the glasses of gravity. Thanks. And we thank the organizers and the institutions there.
What is the speed of the gravitational waves? If she's looking at for the light, that means that that's traveling at the speed of light. Do you assume that the gravitational waves are also traveling at the speed of light?
So yes, we do think that the light is also, well, we believe that gravitational waves are traveling at the speed of information, which is velocity of light. That probably won't change, but it could change. However, it doesn't mean that we have to instantly look at this event, otherwise we won't see it. So, like a bomb, it gets brighter with time, and that time is actually controlled by the elements that are created in the bomb. And so that's why we have about a week or so, or a few days to observe this event.
Maybe, it's a question for us. You're looking for the light from these events, and you say that you're looking for the events of neutron stars. But, somehow it seems that these black holes, when they collide and they make this big splash, it should create light even though they're black holes, because I guess around the black hole there's a lot of stuff that would probably be shaken up by that.
Yeah, so that's a great question. The question is, why don't colliding black holes seem to have this electromagnetic counterpart that neutron star collisions have? The main reason is that everything within the event horizon is not going to escape, and so you're not going to get any energy output that way, and we need a fusion of elements. However, you're correct in saying that black holes may have just kind of things hanging around them in the form of what's called an accretion disk. So just material that might be accreting onto the black holes and they form a disk. It's possible that we could detect this, however, that's not a lot of material in most models, and so it's very unlikely that we'd be able to see it with the telescope, any telescope that we're using right now.
Do the waves dissipate in distance? We're just talking like these are hundreds of thousands of light years away, so one more closer, does that make a difference?
So the thing is, as I said, gravity is a weak force. So they don't dissipate, or they dissipate negligibly. And this is, of course, something to test. You never assume things in physics. But the first order, I mean, we expect them to be dispersions, meaning that they will not dissipate by much as they lie on detectors, even in the most opaque regions of the universe.
Right. Actually, kilonova, what you see today is basically infrared light. Is that right?
Yes, we have not seen them.
Is it because those events are like the billions of light years away? They have redshift to them. That's what you end up today, right? Not the original.
Yeah, that's a really great question. So the question is, are they red because of the true nature of the elements, or are they red because they're so far away? We didn't talk about this concept, but if things are far away, they actually appear much redder than they are in reality, and that's called a redshift. So he's asking, are they red because of the redshift? So no, LIGO is limited to a pretty small area around us, so just like hearing becomes softer with distance, the gravitational waves become softer with distance. And so we're limited to a very small redshift. So that they are intrinsically very red, and that's because they're producing lanthanides, so these very heavy elements, and those happen to have, when you shine light through them, it only leaves the very red light. That's the very basic explanation.
Okay, that's a question for both of you. What would happen if now, with LIGO or the more improved LIGOs that come, we see two events very close in time, like a second apart?
So we filter the data so well in that regard that we should be able to tell even the two signals apart. Because this type of filtering actually filters already lots of noise. So telling two waveforms apart is an easier task because you already know how the waveforms look like. So you can just subtract that off and check.
I'll just adjust the question a bit. What I meant is that the two events are statistically not very probable to see two events very close apart, very, very close. So maybe it's some kind of effect that you also see in gravity, those maybe what I'm asking is, do gravitational waves bend like light because of gravity?
So the thing is, gravity is technically a non-linear theory. So meaning that gravity itself affects gravity. So in that regard, yes, I mean the gravitational waves are also they do affect each other. But here, when we say gravitational waves, we actually mean the linearized portion of that, where the gravitational waves wouldn't affect each other.
Okay,
So they are in the linear limit
if
here.
we see something like that, it could be an echo of a single event. It could be very exciting.
Yeah. The question is, can we see two very nearby events in time? And the answer is yes, of course. I mean, the likelihood that the background will fluctuate so as to give two very nearby events is even smaller. So that would be easy to detect.
Let's say gravitational waves. Do we think of gravity of itself as a force that moves with like a wave like light does, or are you talking about what working space?
Okay, so the gravitational wave does propagate just like the electromagnetic wave, but the underlying theories are different. So the ways, the independent ways in which they do so is different for the two theories. Technically speaking, in electromagnetic theory, we describe things as vectors, like the electric field and the magnetic field are vectors. They're embedded in a, again, just for the interested, they're in a larger framework, just like you could describe these electric and magnetic fields just like the gravitational wave, but they're spins, and spin is the only thing that I will not explain. They are different, okay? And just ask me afterwards if you discuss.
In the interest of time, we should cut the question short for right now so we can get on to the demonstration. So let's thank our speakers, and if you have to leave,
Yeah, so yeah, I have not
Yeah, well, this is a demonstration. We're going to start on interstellar and I guess talk through. Oh, okay. Okay, cool. I will be like 20 minutes or so. Okay, cool. Thank you. Oh, you can just set up with people in front. That would be great.
keep an eye on it.
Yeah, okay, great. Yeah. It's short because the document is so completely it's one we actually so they are representations but the point that they detected is within that would be other units that is very much okay, so that's yeah, and that's completely controlled by that's why people see actually, we only have to work until 9. Oh, yeah, after that, yeah, should probably get
So, for those of you who have already watched, I will just remind you what you're watching. So basically here, there's a spacecraft, and they're flying into a black hole, and then they will use the conservation of momentum to actually fly apart from the black hole, but they will have to sacrifice something. That's going to be the future robot so here I just wanted to show you the black hole itself, because basically this can be real at some point in the future, not very close, but at some point in the future. Hopefully you get the scene where they actually show the black hole. So there you will see the stream of light. That stream of light essentially shows you how space and time is bent around the black hole. So the black hole is what you can't see at the center. So it's not something interesting, it's just a black sphere. What you see is the light, the tube of light that is bent around the black hole. Let's wait for that scene. Yes, you see here, okay, let me just stop here, okay. So here you see the black hole. I mean, the black hole actually is just the region inside this thing. What you see at the edge is the tube of photons that is kind of capped around the black hole. Because right at the edge, the photons really can't go into the black hole, but they just can't go out of the black hole either. So there's actually an accumulation of photons. The photon is essentially light. So you see a very bright region there. And then there are all the background sources of light, like the universe is full of light, right? So I will come to it. So the universe is full of light. So you see the accumulative, the light sources of light in the universe in the background that are kind of focused onto a stripe around the black hole. That's a very nice view of a black hole because it tells you essentially you don't actually see the black hole. What you see is some twisted version of the background light. That's important. And yeah, let's get.
Okay, so you almost kind of answered my question, but just to elaborate. I was first looking at that, figuring that sort of the curvature of that path was the arc of the photons going around.
Yeah.
But I mean, it seems like what you're seeing is a scattering effect, and or is that just visual for the movie? So you can see photons going in that arc path around the black hole, but in order to see it, it actually comes at you. You see what I'm saying?
And it does eventually because it's curved. That photon eventually makes it to your eye. I mean, it's not fully trapped. I'm just saying it may probably makes a couple of turns around the black hole before it does.
Sort of lens.
Yes, of course, it's totally lens. It's yeah. Yeah, it's not a trivial picture. It's not like some type of source is being deflected in a trivial sense. It's a mess essentially of it's a total mess of the background light. And Ashley, you want to come up there? You might answer.
What was the, I didn't quite understand what the trajectory of this spacecraft is as it nears, as it comes near. It is on a parabolic type of.
I guess so.
If
I mean, they don't make.
Yeah.
They don't make such things public, but I assume that it should be somehow. They're
Sort of
getting close. Yeah. I mean, I will let it finish, but if you have questions, you can answer them on this image first. And then.
Were you trying to explain both the outer bright area and the dark, and then the screen bright area?
Right. So this takes me back to the statement that it's more complicated than just a background source being lensed by the black hole. This is the simulation output, and it's hard to pinpoint like what's what. Actually, it totally depends on what's in the background. So, but one thing that I will emphasize is that very serious physicists like Kip Thorne actually worked on this project. So they hired him, the filmmaker hired him to make a simulation. Well, it was already his research project, but he actually ran some code to predict what you would see. And this is an accurate, almost accurate description.
Top light. Dark theory. Top light. Dark theory of
After this point, of course, it's metaphysics.
Yeah.
You never know what's inside of it.
How fast is that spaceship going?
Well, it has to be extremely fast by the way it reaches the black hole because it's losing a lot of gravitational potential energy. So that has to go into kinetic energy somehow.
So does general relativity affects, would they affect the way they would see this black hole? Because they're going some portion of the speed of light.
I mean, so the thing is, to start, they would essentially be elongated like a spaghetti because of the tidal force. I mean, the film, of course, tries to make a story out of this, so they neglect such obvious facts. But apart from that, yes, there would be lots of gravitational redshift, so probably the frequency of the light they see would probably be like redder and redder.
And the clocks would be much slower.
Yes, but with respect to the black hole, like internally within the spacecraft, they would just be normal.
Yes.
Concerning what's in the black hole, Stephen Hawking argued that once information gets into the black hole, it's totally destroyed. It's not retrievable. However, other people argue against that, and it seems it's instead of something. In other words, whatever gets into the black hole is theoretically retrievable, rather than being totally destroyed, as Stephen Hawking said a few decades ago. Can you just clarify this?
So I don't know so much about this. I know a little bit about the work of Andy Strominger at Harvard. And the basic idea is that in very vanilla GR, black holes should only be described by a few parameters, the idea that there's spin and their mass. However, there's this new theory that perhaps these can be actually extra information can be stored within a black hole. This is known as extra hair on the black hole. In this way, there is no loss of information. From what I understand, it's the very beginnings of a new theoretical framework that's being actively worked on. I don't know, and there's no exactly, right now there are no observable predictions of this theory, so I don't know so much more about it.
And then let me just restate the problem. The problem is that black holes do evaporate because they radiate. And once they radiate, you can imagine if you wait long enough that the black hole eventually evaporates, so you'll ask the question, okay, where did the information go? Because the radiation that it produces is thermal. Thermal being, it's like you just can't reconstruct what went in because it's thermal radiation. That's the problem. That's the statement of the information paradox.
Or maybe at the point that it's totally evaporated, the singularity would release all that information.
Sorry, what?
Maybe at the point that it's totally evaporated, the singularity would contain all that information, would release it.
But there will be no singularity left.
So
because the black hole will have evaporated. I mean, we don't have a clear theory of that type of physics. That's called quantum gravity, and we don't have a consistent theory of quantum gravity. Yeah, so it's almost 2 hours, so if you have
you can drop off your surveys at the front table, please. Thank you.